picking up where we left off, here's part D in our chain rule examples. G of x equals e raised to the tangent of 5x to the third. All right, a lot going on here. Okay, so in this example, you can see there are three parts. There's an e, there's a tangent, and then there's 5x to the third. So we're going beyond just two levels of the chain rule now. There's an outside, there's a middle, and there's an innermost, an outermost, a middle, and an innermost, if you will. Which is which? The innermost is the 5x to the third. That's inside of tangent, and that whole thing is in the exponent of e. The middle is the tangent, and the outermost, in this case, is the e. Now, this can throw people. We just saw some examples with powers, and it was always the power, it was the exponent that was on the outside, right? So that very first example we did, x to the third plus 1 to the fifth, right? That felt like the opposite, right? This was the inside. This was the outside. But now we're saying, no, actually the innermost, you want to start with the exponent, and it's this that's the outermost. Okay. When you have something like an e, this is the one exception with the parentheses. Whatever's up in here is the inside, right? So if you thought of, just in its simplest form, e to the x, right? If you were to plug a number in, it would go there. The exponent goes into the power of e, and then you can, if you plug a number in, then you can compute. Where here, if you were to plug a number in, it would go into the base. You would figure this out, and then you would raise it to the power. So that's going inside and then being raised versus going in. It's like, where is the variable? All right. The variable, that's another good way to point it out. The variable itself always points you to the inside, or here the innermost, and then you kind of go back, one level and then another level. Okay. Hopefully that makes sense. Let's take the derivative. So we're going to start with the outermost, and then we're going to work our way in. So I didn't write anything to start this off just because there's so much. Let's talk through it. So g prime, okay, the outermost. Hey, what is the derivative of e to the x? That derivative is just itself, right? Okay, so the derivative of the outside function, since it's e raised to a power, it's just itself. We're going to copy everything. The derivative of e is itself. But there's more to it. There's a chain rule, right? So now we need to multiply. And we need to look at that middle function, tangent. You guys remember the derivative of tangent? It's secant squared. Okay, so we got derivative tangent is secant squared, and then we're going to copy the 5x to the third. And then finally, we're going to take the derivative of the innermost, and that's 15x squared. There it is. Derivative of the outer, the middle, the inner. If this was a test, you could leave it just like that, no problem. Truth is, there's really not much to clean up. I think I wrote it in a different order. In this case, we would typically put the 15x squared in the very front, then the trig function, and then the e on the very end. That's just kind of what people have agreed to do with these three things. You would see them in this order. I don't think we can really argue it's simplified better. Okay. Let's take a look at another one. So if that E was confusing in part D, let's look at a simpler version of that, much simpler version. This will only have the 2 levels in the chain. H of x equals E raised to the 2x. Make that a little bit darker, 2x, okay. And so, as we discussed, the 2x is actually the inside, and the E is the outside. It's in the power of E. So if you kind of like, the help of where are the parentheses, right? Even in the exception with the E, if there were to be parentheses somewhere, where would they go? And wouldn't you put them, it seems kind of weird, but you would put them around that exponent that way. This would mean the same thing as this. And so maybe you can see, oh yeah, that would be the inside, and then that's the outside, right? That's kind of the way it would fit. Although, we really don't use parentheses there because we all understand that that's in the power. Okay. So how would this derivative look? And I think oh, okay, it's blank. All right. H prime of x. So we start with the outside. Well, the derivative of E, we know, is just itself. So we're going to copy the whole thing, e to the 2x. Then we're going to multiply by the derivative of the 2x, which is 2. And there it is. This case, let's go ahead and write it a little bit neater. That looks good right there. 2e to the 2x. Put that 2 in front. Okay. Now for this example, this is going to be a helpful discussion of higher derivatives. So it's good to kind of go back and talk about that e again, sort of in a simpler case. But I want to highlight something even more. What if we wanted to take a second derivative? Ooh. Okay, there's going to be a pattern here. It's kind of cool. All right, so if we look at our simplified version, so we have now a constant multiple, so that would just kind of tag along. And then we have e to the 2x again. Well, if we need to take the derivative of e to the 2x again, it's going to be e to the 2x times 2, just like before. This would simplify to 4e to the 2x. Okay, there's your second derivative. Hey, what if we wanted to do a third derivative? This is the last one we'll do. A third derivative. And maybe you kind of are picking up on the pattern. What's going to happen if we take a third derivative? And, even back from here to here to here, we're just going to multiply by the 2 again. Just the nature of the e and the 2x. We're going to multiply by 2, multiply by 2. This is going to be 8e to the 2x. But if you want to see the steps, hey, the 4 would come down, and then the derivative is e to the 2x times 2. One more time, and now, well, there it is. 8e to the 2x is your third derivative. We could keep going. Fourth derivative would be 16e to the 2x, and so on. Okay, so kind of a nifty, simple pattern there. All right, I got one more example, and this one abstracts the idea of the chain rule a little bit. I think there were homework questions of this sort of this same nature with product rule, maybe quotient rule as well. Be good to do one together here. It says let r of x equal f of g of x, the composite function. Okay. Looks like I need my paperweight again. Where g of 2 equals 3, g prime of 2 equals 5, and f prime of 3 equals 6. Well, okay, I guess. Find r prime of 2. All right, well, let's see how this plays out. To find r prime of 2, we first need to find r prime of x. And once we have r prime of x, then we will plug in the 2, and these other pieces are gonna be helpful. So I ended up running out of room on my page, so I've got the final answer here. Just ignore this stuff for the moment. All right, so based on r of x equals f of g of x, r prime, well, this is exactly the chain rule, the definition of the chain rule, if you will. It's not the definition. I shouldn't say that to be confusing. This just is what the chain rule says. Okay, r prime, f prime of g of x times g prime of x, right? But we want to know r prime 2. So we're going to plug in 2. And that means we plug in a 2 for all of the x's. So it goes in there, it goes in there, and it goes in there. All of the x's become a 2. Okay, and now here that other information is helpful. G of 2, they said is 3, so this will become a 3. G prime of 2 is 5. Okay. So that's a 3, that's a 5. Okay. And finally, oh, what do you know? This created f prime of 3, and they told us that that equals 6. So that brings us to our answer. 6 times 5, well, r prime of 2 must equal 30. And this is kind of a nifty way to give you a chain rule problem, without, kind of in a different, from a different perspective. And yeah, that's good. Okay, let's stop this video here. I do have one more part to, this is the end of the examples. I have one more part to the chain rule, looking at the Leibniz notation. So if you, I recommend everybody watch that last video. I'm not going to make it optional. Watch that last video, everyone, so you can understand a little bit better Leibniz notation.